here. So frame of reference is what we require some observer to observe any kind of motion. Suppose if we are observing something, so we are means we can be taken as our frame of reference. Okay, so observer is situated and make his observations. That is known as frame of reference. Now, in this frame of reference, uh, the observer who is observing it, he may be in rest or he may be in motion. Now, based on that, we have two types of frames of references. Okay, so one is inertial frame of reference, inertial frame of reference. Next one is a non-inertial frame of reference. Whatever observation we are making, the observation which we are making, if we are at rest, if we are at rest or if we are in uniform motion, then such a frame we can be taken as the inertial frame of reference. If the observation from wherever we are making, if we are in accelerated motion, if we are in accelerated motion, then such a frame can be taken as a non-inertial frame of reference. Okay, so if uniform motion or at rest, based in such a location, if we are making observation, then that can be taken as a inertial frame of reference. If the frame of reference, the observer who is observing the motion, if it is in accelerated motion, then such a frame can be taken as non-inertial frame of reference. And here, whatever inertial frame of reference is there, here all the laws, whatever Newton's three laws we have studied in previous classes, all the Newton laws can be applied here, where in inertial frame of reference. Whereas in non-inertial frame of reference, Newton's laws are not applicable. We cannot apply Newton's laws because already the frame where we are, that itself is in accelerated motion. So we cannot apply Newton's laws of motion in case of non-inertial frame of reference, right? So that is about a non-inertial frame of reference and inertial frame of reference in brief. Okay, so inertial frame means what? Wherever we are observing from, if the observer is at rest or is in uniform motion, that frame can be taken as inertial frame of reference, right? So where Newton's laws can be applied. So this we will come across. And whereas non-inertial frame means if a person is in circular motion, then that can be taken as non-inertial frame of reference. Suppose we are on a joint wheel and we are observing some things which are going around. Then the frame which we are in can be taken as a non-inertial frame. Otherwise, if we are in a lift, when the lift is in motion, it moves up and down. So such a frame can be taken as also non-inertial frame of reference. Okay, for those things we cannot apply Newton's laws easily, right? That is about the frame of reference. Next, we will go with a topic called impulse. In this generally we come across this in our day-to-day life situations also. Like suddenly, if large amount of force if it is applied, that means in a very short interval of time, if large amount of force is applied, such a force we call it as impulsive force. Like uh, examples if we go with, like when we are moving on bike, suppose nowadays if it is rain, now rainy season is taking place, so suddenly if there is a pit, if we are moving very fast, if we enter into that, what happens? If there is no shock absorbers, we may fall down immediately and the bike will get damaged and we also get injured, right? So to avoid that a large amount of force in short interval of time, there some springs will be there in that springs we call it as shock absorbers. Okay, so impulse is what? It is a large amount of force if it is acting for a short interval of time, very less time. Such a force we call it as impulsive force. Now, So slight difference will be there, impulsive force and impulse. Impulse is what? The how this large amount of force is acting for a very short interval of time. Okay, the force into very short interval of time, we take it as a impulse. Now already we have got this relation, F is equals to dp by dt. We have no from Newton's second law. No, so dp is equals to what we can write, F into dt we can write. Okay, from Newton's second law, whatever we studied from there only I'm writing. Now, whatever force acting for a short interval of time, dt I'm taking means the time interval is very small. Okay, this we take it as a impulse. Okay, this force is only we are considering it as impulsive force when time is very small. Now, so impulse is what? Force for a short interval of time. Now this impulse is becoming equal to what? Change in momentum. Okay, so impulse, if we want to measure impulse, we will be measuring change in momentum only. Okay, and when it comes to units, okay, when it comes to units, the unit of impulse and unit of momentum will be same. Okay, now so already we have a unit of momentum as kg meter per second. Okay, kg meter per second is SI unit of impulse, whereas from this formula if we write unit, what we can write, force unit is Newton and time unit is second. Newton second is impulse unit. So the same thing can be written for linear momentum also, Newton second. Okay, so there we didn't describe in terms of force, that's the reason I haven't written there. Here we have got one formula based on that I am writing Newton second, right? Now CGS unit, what happens, gram centimeter per second, dyne second we can write. Okay, better that also I will write. This is SI unit and CGS unit is what? Gram centimeter per second or dyne second, right? So this is SI unit. Next, what about dimensional formula? Dimensional formula also we have written already, same thing I am following here. M L t to the power of -1 is dimensional formula for impulse, right? Now, um, generally this is impulse. So if we write an expression for impulse, impulse is also vector quantity. I bar is equals to, what do we write, integration. So because this is a small quantity, for total quantity if we write, we will be integrating on this F into dt we will write. Time is anyhow scalar, force is vector. Okay, F into dt we will write. Now, as it is taken in terms of time, t1 to t2 we will take. I said integrations when I am speaking about equations of motion by calculus method. There I said about integration and differentiation in short, right? Now, so that is about how do we write an expression for integration in integral form. How to write an expression for impulse in integral form. Okay. Now, so this is a impulse expression mathematically and unit and dimensional formula. Now if we take force and time graph, impulse is equal to the area under force and time graph we will be writing. Okay, suppose let me take another page. Suppose if we have an object is applied by some external force, and in that force versus time if I take graph, force versus time if I take graph, and this side I am taking time and this side I am taking force. Now the graph, if it looks like this, suppose the graph looks like this. Now, so if I want to know the impulse, only I have some variable force and time with respect to time. So for that variable force and time, if I plot a graph, so I got a graph like this. Now, if I want to find impulse from the given force time graph, what do? We will be just taking area under the impulse, area under the force time graph, which gives us impulse. I am drawing one line over here and I will be calculating area under this. Okay. Now, so this area gives us impulse. Okay, area under force time curve gives us impulse. Okay, now how do we calculate this? impulse is equals to Impulse is equals to area under force time curve we said, right? Area under ft. Here it may come, it is coming as a straight line, but other graphs it may come as a curve also. So that's the reason ft curve I am writing. Ft line also we can write now. So what is that area? It is becoming a triangle. So what we will write? Half into base into height will write it, right? That is what, as we got a triangle here, for this we can write it now. So half into base is what? Time, right? And height is what? Force. Okay? Half into f into t, we will get it as a impulse. So this is how we calculate impulse if there is a force time curve. Okay, now if we want to write a average magnitude, so already we have impulse formula. Just now we have written t1 to t2 f into dt. Okay, so when force is variable we are writing all this. Now if the force, if we want to take it as in an average, okay, so f is some average, f average if we take in short, this is some shortcut method we can treat instead of taking all this. So what we can write, f we can f average directly we can write instead of all this integration formula under this f average into integral t1 to t2 dt we can write. Okay, so this f average into delta t we can write. This is for impulse. Okay, so simple, already we had this formula. Now for that what we are doing, f I am taking it as some average of value, f average. So average value means it will be no more a variable, so we can fix it out. And integration I am doing to dt. So this dt value also I am taking some change in time. Okay, right. So that is about force. When force, if we take, when force is taken in terms of average, we will take in, we will calculate impulse in this particular way. Next, from Newton's second law. From Newton's second law, if we write, let me go with one more page. If we have a graph, same force time graph only I'm taking here. This time I will take like a curve. Okay. As usual, on x-axis we will take the time, and on y-axis we will take force. Okay. So if we have a graph like this, suppose if we have a graph, I have to draw it smoother. The curve should be smooth. Just hold on. Right, so it's fine. Now if we have a graph like this, so this force is what is happening, force is increasing again decreasing. So in an average, somewhere here I am mentioning average value. So here whatever value we are taking, force average value I am taking over here. Now so what we will write from second law, Newton's second law, F is equals to dp bar by dt will write. This is what from Newton's second law what do we get? And from here, so if we make integration on both sides, t1 to t2, because as force is variable, f into dt means this dt I brought this side. Next integration dp. Okay. Now so this what we call linear momentum also changing from p1 to p2, as it is a d has come means it is variable, and here time is variable, so t1 to t2 I have written. Now so what we can write from here, integration f dt is what? Our impulse. Okay, I, and right side what we have, integration of dp means p we will get, and when we are substituting limits, upper limit is p2, lower limit is p1, p2 minus p1 we will be getting. Okay, now so this I can write vector form. No, so what do we got? Impulse is equals to change in momentum we got, right? So this I said it again, I just wrote an expression for it. Change in momentum we can write. That is, so if impulse, if we want to calculate, which is equal to change in momentum, linear momentum has to be calculated. Okay. So this statement also known as impulse momentum theory. Okay. Impulse momentum theorem we call it. Okay. So this is a little extra information only, but still I'm giving it. Okay. Now, what are the applications of it? What are the applications of it? And how to decrease this impulse, that we will see. Now suppose as we are watching presently IPL is going on, when batsman hit sixes, if it is not going out of the boundary, if somebody is trying to catch it, what they will do, they will try to move their hands a little backward. Why they will try to move little backward is, so when force is acting for a short interval of time, this we call it as impulse, no? Now this time, what happens when they are pulling backward, little backward, this change in time little bit it increases. Okay, so we are increasing the time when we are increasing the time, so the impulsive force effect will decrease. Okay, that's the reason the fielder who is trying to catch the ball, he will try to pull his hands backward. Okay, so there we are trying to increase the impulse time, we are trying to decrease the impulse effect. Okay, that's the reason he will try to pull backward his hands a little bit. And one more thing, when people are going for this what we call long jump or high jump, what happens after they cross their target, so when they are jumping into that, they will either they will put sand, and whereas in case of international games, what happens, they will put some foam, they will jump into that. Why they'll keep that? If it is not foam or sand, what happens, the place where they are landing, so if it is rough surface, the impulsive force will be high, so there is a chance of getting injured. To avoid that, they are placing some soft material in case of long jump and all. Okay, so that is about to avoid impulsive force. Next, right, that is a, those examples are more than enough. Okay, so that is about impulse and its applications and its different forms, right? So if you, so okay, we will go with the linear momentum, conservation of linear momentum topic, right? So law of conservation of linear momentum means, here the word, one word should be noted carefully. Conservation means we want to, or it has to be remain constant, or it has to be remain same. How much ever is there, that much has to be remain same. Now suppose I am considering some object over here, some small object which is having some mass m, I am considering. Now in that what happens, this object, if it is moving with some velocity, if it is in motion, if it is moving with some velocity, and there is no external force acting on it, the object initially it was applied by some force, and no other external force is acting, it is in motion, then this situation can be taken as isolated system. Okay, isolated means it is separated from all. Now, so what is happening, it is moving, some external force acted on it, what is the external force we don't want here, and it is in motion. When it is in motion, total momentum of this system, if it is constant, then total momentum of this system, if it is constant, then it is said to be law of conservation of, means it is obeying law of conservation of linear momentum. When it obeys law of conservation of linear momentum means, when there is no external force acts, then the object which is in motion can be said it as it is in the, it is under law of conservation of linear momentum. Now according to Newton's second law, what we have, force is equals to rate of change of momentum we have. I am writing differential form only. Now, what we are saying, external force has to become zero to be in to be in conservation of momentum, right? So that is, if F is equals to zero, F is equals to zero, that means what happens? dP by dt is equals to 0. That implies, what do we get? dP is equals to 0. Okay, so when change in momentum is constant, change in momentum is 0 means momentum is not changing, so momentum is what? Constant. This is what we are saying. When there is no external force acts, the momentum remains constant, such a situation only we are calling it as a law of conservation of linear momentum. Okay, now here when law of conservation of momentum is taking place, this law of conservation of linear momentum is independent of frame of reference. Okay, so but whereas linear momentum depends on frame of reference, but this law of conservation of linear momentum is independent of frame of reference. Here from this expression we can write one more. P1 means all the particles. If there are number of particles, we can write for all of them we can write this. We can extend this expression for all the momentum of all the particles which are present in that can be taken as their momentum. Some of their linear momentum also can be taken as a constant. Okay, so that means what we can write m1 v1 plus m2 v2 plus m3 v3, so on. So all these can be taken as a constant. This I am just writing whatever expression we have here. For that I am extending it. Okay. So this is about law of conservation of linear momentum. If only two particles are there, what we will write? P1 plus P2 is equals to constant. M1 V1 plus M2 V2 is equals to constant. We can write. Okay. For that, if you write, so I will take it in next page and I'll try to finish it out. So what is happening? Only two particle system if we write. What do we write? P1 plus P2 is equals to constant we'll write. Right? Now, so in this, what do we write? M1 V1 plus M2 V2 is equals to constant. Right? Now, so what else we can write? M1 into uh, anyhow it is constant. I am differentiating it, dv1 by dt, differentiating with respect to time, m2 into dv2 by dt I am writing. Okay, this is anyhow constant. Differentiation of constant becomes a 0. This side also we have to differentiate. D by dt I am applying on both sides. This side is 0. Now, so m1 into dv by dt is what? Change in velocity, right? Now, so change in velocity means change in velocity by time means acceleration. m1a1 plus m2a2 is equals to 0. Now m1a1 is equals to minus m2a2. So that means m1a1 is what? Force formula. F1 is equals to minus F2. Right? From law of conservation of linear momentum, what we derived? Action force is equals to reaction force. From Newton's third law is derived from law of conservation of linear momentum.